new station, which is called KMRS. And I found a new city on the Korean map of algebraic geometry, Jeonju. And so I would like also to speak about something very new, something that is still under under development, and it started only 3 months ago. But maybe even before that, I should mention that everybody here understands the meaning of KMRS and algebraic geometry, but maybe not all of you know what is symposium. And because Greek is not studied in Korean schools, and so may I explain that symposium is a word consisting of 2 parts. Sim is the same as in symmetry, and the translation is that of the word symposium is drinking together. And this was an important ritual in ancient Greece. About that amount of people gathered together, and they were drinking and eating. Senior members, unlike here, were reclining on some sofas, and junior people were sitting as you. They were drinking not exactly coffee, because I'm not sure that coffee was that popular at that time, and they were discussing in turn some important philosophical problems. And usually, for example, the most famous example is Plato's dialogue, which is entitled Symposium, and they were discussing the nature of love. And so we're discussing maybe less important problems, but still I can mention what is, in my opinion, what I love in algebraic geometry. I think that there should be maybe 3 ingredients. First of all, the result should be easy to explain to anyone. Second, there should be some general results, but they should manifest themselves in lots of concrete examples that you can check. And also the third ingredient is that maybe there should be connections between different areas of mathematics. And so given that much time, I'll try to show you these 3 ingredients. And so I start with section 1, convex bodies. This doesn't have any apparent relation to algebraic geometry. I recall that we'll consider real space, vector space Rn, and with origin. And everybody probably knows what is complex body. It's part of the space such that any 2 points can be joined by an interval, and the interval is contained in this body. So if you have points x and y, the points of this closed interval, they can be expressed in the form alpha x plus beta y, where alpha and beta are positive or non-negative and do not exceed 1, and their sum should be equal to 1. For example, and these complex bodies are very important because a lot of in our life are described by them, in particular consumption and production. For example, if you can consume only vegetables, and here you consume only meat, then you usually can consume some mixture, which is very popular with Koreans. You mix everything in your dishes. And also, if you can produce, for example, a certain amount of cellular phones or notebook computers or tablet computers, then probably you can adjust your production to satisfy demand, and you can produce any mixture. So this is very important. But there is the points, you consider then the boundary. And the boundary of a convex body X is rather good, because it consists of certain smooth pieces, but pieces of different nature. Here, when you have the boundary that is strictly convex, you have only one tangent space, or if you prefer, only one normal vector. But in the flat parts, when you join, you have here you have your tangent space is not well defined, and therefore the key notion here is supporting space or supporting plane. What is this? In coordinates, we can write it's as follows. A hyperplane can be written like this. And this hyperplane with the quality here is called supporting hyperplane if X is contained here in this half space, and you have a quality for some point on the boundary. So this is supporting hyperplane, and this is supporting hyperplane, and there are lots of them. So I use this normalization because I would like to have a well-defined point in the dual space. So I can denote this by X, and we can write by alpha, and we can write this for X in X, and we have equality somewhere. Then it's clear that this point X where we have equality lies on the boundary, and we get a set of hyperplanes in the dual space. Now we assume that our convex body contains the origin. This all is not probably very important, but if we'd like to use vector space and not projective space, then it's convenient. And then the locus, we now consider the locus of supporting hyperplanes. So it lies in the dual space, and I give the following definition or definition proposition. I denoted it in such a strange way. It's not accidentally, because it says that this locus is the boundary of some X star, where X star is a convex body whose boundary is the locus of supporting hyperplanes. So maybe I should illustrate this by some examples, easy examples. Take the plane and take a square where you have here -1, -1, 1, and 1. What should be this thing? And I didn't say, I believe that in this case, X star is called polar, or I prefer saying dual, convex body to X. So what should be the dual? And I just draw it in the same coordinates. It should be a diamond like this. And furthermore, the vertices of our square correspond to the edges of this dual, and vice versa. The edges of our square correspond to vertices. What I mean by saying correspond, I mean that they support at the corresponding point. For example, here we have only one supporting hyperplane in such a point, in such a point, and here we have a lot because all these are supporting hyperplanes. And in this way we get an edge. So I list some properties of this. Well, first, some properties, or some examples also. If you have a sphere of radius r, then the dual is also a sphere, but of radius 1 over r. And here we already used that the origin is not there. Now, there is a notion of polyhedron. Polyhedron is the intersection of finitely many half spaces. And then the dual is also a polyhedron, and to faces of certain dimensions they correspond faces of complementary dimension. And in this way it's classical. You know probably that for regular polynomials they were divided in very old times, they were divided into pairs. For example, in three-dimensional space there is tetrahedron, which is self-dual, but for example octahedron and cubes are dual to each other, as well as dodecahedron and icosahedron. So this duality corresponds with this classical notion of duality. Third, any convex body is an intersection of half spaces, but maybe an infinite number. For example, for sphere, you should take the half space defined by the tangent plane at each point and consider the intersection. possibly infinitely many half spaces. Okay, maybe next, if we scale up our body X, then the dual body scales down, which means that if we multiply it by some lambda, the dual body multiplies by 1 over lambda, as we saw in the case of sphere. By the way, the same we can do with ellipsoid. Now, if Y belongs to X, then X star belongs to Y. Y is in Y star. All these are easy to verify, and if you play with it, you can find a lot of examples. But maybe one of the most important properties is the duality, reflexivity. If you take a convex body and consider the dual to its dual, which lies already in our original space Rn, then we get the same thing. And actually, the proof, I can formulate a more precise statement, because here we actually had the duality not because these convex bodies, but rather between their boundaries, because the supporting plane also touches the variety at the boundary, because this follows immediately from the definition. And then we define this dual body as the body whose boundary is this set of supporting hyperplanes. And so we can introduce the incidence correspondence. It's a set of pairs, a set of couples, which lie in this product of the space and its dual, and actually alpha lies in here, X lies in here, and X is a contact point of alpha and X, where of course the contact point is the point of intersection of our hyperplane and the convex body. And then we have of course projections, projection P to here, and projection Q to here, and one has the following proposition. That we have the following equality, not just isomorphism, but equality. That the incidence correspondence constructed for the dual variety coincides in this product with the incidence correspondence for the original variety. And I recall you that for Rn double star is the same as Rn, so this is obvious. And from this follows reflexivity. Now, supporting hyperplanes are very important because important in mathematics and important in life, because if you have a convex body, be it consumption or production, for example, then you are interested, if you are a producer, you are interested in maximizing your profit. And your profit is a linear function, and you need to maximize it on a convex body, so you get a supporting hyperplane. And the same for consumer. Consumer wishes to minimize his expenses, and so we again come to the same problem. And there are lots of software, for example, mathematical tools to construct supporting hyperplanes. But we would like to have some mathematical results, and here I proceed with the mathematical result that we need. But I first need some definition. It has two parts. First, suppose that we have a point in the dual, and then the variety, not the variety, but the phase, which can be defined like this, is called the exposed phase of X. Exposed phase of X with respect to alpha. So looking here, what is this exposed phase? This the set of points of X where alpha is the supporting plane. And for example, if you consider this example of square, then for certain alpha, each edge is an exposed phase. For other alpha, for example, for such alpha, only this vertex is the exposed phase. And second, let R be a non-negative integer, and then X be a point of the boundary of X, and it's called R singular, if I'll explain this, and the set of R singular points of X is denoted by like this, with angular brackets. So what do we have here? We take the point, if we have a smooth or strictly convex point of the boundary, there we have only one supporting hyperplane, namely the tangent hyperplane. And there is only, for such a point, we have 0 here. The dimension, there is only one point, which means zero-dimensional variety. Zero-dimensional point of the, just one point of the boundary. But if we have a point like this, we have a lot. And the dimension of this lot is called R, so this is an R singular point. So the R singularity measures really the singularities, the dimension of the set of supporting hyperplanes at this point. And so we have some results concerning this R singular set, and I'll formulate it. It's an old result, and there are some problems with this, which I'll explain. So, theorem. This theorem belongs to Anderson and Klee. And if I remember correctly, it dates back to this year. And it says that the dimension of the set of R singular points satisfies this inequality. And this is a really old result, and I must confess that I haven't yet seen their paper. And the problem is that they consider also infinite dimensional case and non-compact convex bodies, and they use not the dimension, but they cover the subset, but by possibly infinitely many subsets of fixed Hausdorff dimension. That Hausdorff dimension can be real, not necessarily integral, and so on. And but in our case, dimension is suffices, and so I wrote it like this. And I think that even one can show, but this I didn't verify, that if this isn't the theorem, but I think that one can prove this. If we take a general point here, then the tangent space to the set of these R singular points at this point X is orthogonal to this. Let me explain what it means. Here we have some face of the dual body, which consists of supporting hyperplane set X. And here we have some smaller convex body, and we take the tangent at a general point. And then from this follows this inequality. And there is another point which I didn't check, but all these people they consider the situation as I described it. But I think that maybe for us, algebraic geometers, maybe it's better to consider projective space corresponding to R, because there are many indications that some properties become more uniform from that point of view. Of course, if you consider such things as production, for you it isn't the same to produce 2 times more these fixed amounts. But if we consider geometry, then maybe it's better to consider the projective space, but I didn't check all statements in this case. Okay, so here ends the first part.
May I ask you a question?
Yeah.
The set of R singular points has some kind of variety structure?
A singular point? It's not variety. It's, for example, in the case of polyhedra, it's a polyhedra.
For arbitrary convex body.
It is, of course, for each hyperplane, the set of the exposed face is a face, and then you have a union of faces. That's what you have.
I mean, it's a set, but I don't know how to write dimension.
It's not a set. It's for example, take a cube. Then for r equal to 1, you have the edges, and for r equal to 2, you have vertices. So that's like this. I wouldn't like to go into these details, because if you want to consider something very, very general, then you will be faced with the necessity to consider something like Hausdorff dimension. But in our setting, you have this is compact, X is compact, and then you have finite union of some convex bodies, and that's okay. So now we would like to study something similar in the case of
What's the small n? Small n is the dimension of x.
Small what?
N, yeah.
Sorry, there is no small n. Thank you. Thank you. Just because first I wrote n small, which seems natural, but after that n will be n capital will be the dimension of the ambient space of a variety, and then it's better to use this notation. So this x lies here.
X is not degenerate, right?
X is a body, which means that the dimension of x is also n. Yes, it's like square in the plane. It's okay. So next step is to consider a similar problem in projective geometry. So here we consider a non-degenerate, maybe smooth even for simplicity, non-degenerate in the sense that we discussed at the first lecture, not contained in a hyperplane. Smooth variety. But here the dimension is can be smaller. It's not a body, and so we should define what is a tangent hyperplane. We have at each point we have this, say, projective tangent space, and if we take a point alpha in the dual space and consider the corresponding hyperplane, which can be defined like this, then H is tangent to X at X. If H contains the tangent space. So at each point there are many, but these many are described by a linear space. So at each point we have this space of tangent hyperplanes, because these are the hyperplanes that pass through the tangent space, and this can be denoted like this. Now we consider the following subvariety called conormal subvariety. And it's defined as follows. It's the set of points and hyperplanes such that the hyperplane corresponding to alpha is tangent to X at X. And we have two maps, two projections, one onto X and the other Q in here. And the image of the second projection is defined defined to be the dual variety to X. So we can write here X star. So what are the fibers of P? This is a fiber bundle in the smooth case, and I already wrote these fibers are like this. So since the dimension of X is small, the dimension of this conormal variety is n minus 1. And so the dimension of X star is really a proper subvariety in the dual space. And usually when this map is generically finite, you expect that this is a hypersurface. And this is also a very old topic to study. Formally, in the case of curves, plane curves, they were introduced by Poncelet. And he did this work while he was in a Russian prison because he participated in Napoleon War, and he was caged, and he spent a winter near the town of Smolensk, and he had nothing to do. Probably the conditions were good enough, and so he did this, also with some mistakes, but later he became, when he returned to France, he became president of some military academy, I believe, and he only published this work maybe several dozen years later. And so why are this interesting subject to consider, even in the case of plane curves? Because actually the singularities of this dual variety correspond to some special tangencies of the original variety. For example, if you take C to be a curve of degree 3 non-singular elliptic curve in the plane, it's smooth, but it has a certain number, 9 inflections. And to these inflections, they correspond in the dual curve, which has degree 6, they correspond to certain cusps, 9 cusps. And so you see immediately what some unusual, peculiar points, peculiar behavior of tangents you see in the dual variety immediately. And one of the main theorems about the dual variety is the following reflexivity theorem. Again, and even yes, and maybe I should have said that even if X is non-singular, then you can consider this correspondence in the non-singular point and take the closure in this product, in this definition. And then you can define dual varieties even in the singular case. And then you can, although the dual variety may be singular, and is usually singular, this makes sense. And to prove this, again, you can show that this conormal variety for X and for X star, they are the same, they are equal. And this implies this. It is interesting to study the singular points of dual variety, which exist usually even X is non-singular. And one can prove many theorems about them, and put some conjectures, but maybe I will concentrate on a different thing, and I give a definition, which mimics the definition in the case of convex body. So let alpha be a hyperplane, a point of the dual variety, a tangent hyperplane, and consider this scheme. What does it mean here? It means that we consider all the points, geometrically, we consider all the points at which this given hyperplane is tangent to x. But as we will see, usually this very often this is not reduced, so you should speak about scheme. And then this is called the contact or tangency locus of alpha. And we say that a point alpha in the dual variety is called weakly asingular if the following is true. And here I must say that in the case of convex bodies, this tangency, or this locus where it is supporting, it's always a polyhedron of maximal dimension, and so it's the same as a linear subspace. But here, of course, this tangency locus is not something linear. It may consist, for example, of several points with multiplicities, and we take the linear span, which I denote by angular brackets. And the condition that it has dimension at least R, as in the case of convex body, where this angular brackets mean taking linear span. And the locus of weakly regular points, weakly asingular points, is denoted by like this. So we consider in the dual varieties, the subset of points for which the linear spans of tangency locus has given a rather big dimension. And now, conjecture. There was, about 2 years ago, a conjecture was formulated about this. And here I must say a few words. But maybe I first formulate this conjecture. Although chronologically, this was the other way around. Conjecture was formally formulated by Roland Aboaf. And it's as follows. Very similar to the case of convex bodies. And the story is as follows, that Ranestad and Sturmfels Sorry, yes, thank you. Because they didn't write W, but I'll explain why it's necessary. Ranestad and Sturmfels wrote some paper where they implicitly used some special cases of this conjecture, maybe not so special, but then they were told that this is not approved because they used something which is not proved, and they circumvented this by giving another proof in the second version of the paper. But in a discussion with them, this conjecture was formulated. And this looks nice and looks very similar to the conjecture for convex bodies, but this is not true. And the first counterexample was given by Claire Voisin. And now I give you some counterexample with an easy explanation why this is not true. So consider cones over hypersurfaces of degree d in Pn minus 1. So we consider hypersurfaces in Pn, which are cones over hypersurfaces of degree d. And they form, one immediately sees that they form a subvariety of dimension and they are all singular, and I'll write where in this variety, where X is the Veronese embedding of Pn, which lies in here. So let me explain this. When you embed X by Veronese map, which means you take all monomials of degree d and consider the image, the hypersurface sections of degree d, they correspond to hyperplanes, and the singular hypersurfaces correspond to tangent hyperplanes to this variety. And so X star consists of all singular hypersurfaces of degree d. And we consider a particular special family of cones. Now, each cone, it's defined by equation, by some form of degree d in x1, xn, but x0 is missing here. We consider now the cone with vertex like this. This is the vertex of the cone to make it concrete. And the tangency locus is defined by vanishing of the n partial derivatives. But we would like to get, and these are equations of degree d minus 1, but to get an equation of degree d, we should multiply by all coordinates. So that vanishing, for example, of this partial derivative is equivalent to vanishing of this multiplied by xi for all I. And why I like this more? Because this corresponds to hyperplane sections in the Veronese embedding. And so, if in the above definition we put nu is the dimension of the ambient space, and R like this, then we get And this means that this conjecture is not true. Starting with d equal to 4 for n equal to 2, or two or 3, or d at least 3 for n at least 4. That means that we have more cones than expected by this theorem. And so this conjecture is false, and the explanation is that the fibers of this map Q contain too many nilpotents. If, for example, we have a cusps of big order, then the inverse image of this map Q has a lot of nilpotents, and this makes the ambient space very small. And now, this seemed to have ended this project for some time, but actually it wasn't the case, because a very different problem led to what turned out to be a similar question. And this problem concerns osculating spaces. Now I give definition. So section 3, osculating hyperplanes. So if we have a variety, again as above, and non-degenerate, even smooth, and we have a hyperplane, which means a point in the dual space, then the corresponding hyperplane suppose that H contains X. Then it has some local equation, and H in particular has some image in the in this structure, germ of the structure sheaf, which contains the maximal ideal X. And so you know that if H is contained in M, passes through the point X, then we say that it's tangent if it's contained in M square. If the corresponding equation, say H, is contained in M square, and we say that H is osculating or osculates at X if H is contained in the cube of this idea. And then we can consider osculation of higher order. So this means that analytically the Taylor expansion here for osculating hyperplanes starts with terms of degree greater than 2. Now maybe I should explain this terminology, particularly because this was present also in the first lecture, what it means, since we already discussed some etymology of the word symposium, maybe we should also discuss this etymology. How a variety can meet another variety. The first case that it simply meets it. For example, like this line meets this parabola. Meets, so to say, transversally. It corresponds, it's similar as if you meet somebody, just pass by in the streets by somebody. Next case is when you have tangency. And tangency corresponds to Latin word tangere, which means touch, to touch. To be tangent means to touch. So you didn't pass by somebody, but you shook hands with somebody. And so this corresponds to tangency. But osculation, there could be more intimate contact, as you understand, when you meet somebody. And here I should use a different picture, because for parabola it doesn't exist, but for cubic parabola there is a possibility to touch like this, very intimately. And this corresponds to osculation. And why I explained the word tangency as coming from the Latin to touch, but osculation comes from the Latin osculare, which means to kiss. And this is, of course, next step of intimacy, because you kiss somebody. And there are also further levels of intimacy, which correspond to higher level of tangency, but probably not in the street. And I will not probably consider them in this lecture. And so maybe the last thing that I'll be able to introduce, what is osculating space? So osculating space, last definition. X at x, will denote it like this. It's the intersection of all hyperplanes osculating at x. And because we know how many partial derivatives there exist, we can immediately give the following bounds for the dimension of it. I'll consider projective osculating spaces. So, of course, it cannot be less than the dimension of the tangent space, because it contains it. But while the dimension of the tangent space for a smooth variety is stable, it doesn't change from point to point. With osculating spaces, the situation is different. At different points, they may have different dimension, and we can only write an inequality like this. Its minimum of this and this, where n capital is the dimension of the ambient space. This is obvious. And this is the number of quadratic forms which you can have, which is the same as second derivatives. So it's in these limits, and one would like to know whether it jumps or not. And the only thing that we can say from the definition, that this function, the dimension, is lower semi-continuous, which means that this dimension can drop at certain closed subvariety, and drop several times. Okay, so that's all for today. And tomorrow I'll try to tie all these pieces together, to bring together all these pieces.